Okay, how are we, people? I'm looking at question 15, 7b question 15. I had another class question about this. I talked about it in the Zoom lesson, but I think we should actually look at it again. I think I can explain things a bit more clearly than I did in that Zoom lesson. And this is really worth looking at. So the reason is because it keeps coming up in your calculus course. So if y equals e to the x, it's quite special. It is its own derivative. It's going to come up again in integral calculus. So it's quite a special function. One way that you could calculate values of e to the power of x is using this summation formula here. Okay? So let's have a look at that. This is the whole thing here. Right? E to the power of x equals the sum of n equals 0 through to infinity. Now those n values, they're whole numbers, right? It doesn't really make that clear, right? And they need to go all the way up to infinity, right? So that you could maybe write n belongs to a set of, now they're positive whole numbers, including the 0. Maybe we could call them natural numbers, including the 0, right? So that's the first thing about the sum notation. And what would it mean? Let's say we want to just find the number e, right? We sort of remember what it is. I only ever remember about 3 decimal places. I think 2 is the next one. So we know the number e. We've been using it at least to a few decimal places. It's on your calculator. Let's say we wanted to compute using this formula just the number e, as in e to the power of 1. So that x would have to be 1. Okay. So you could say, all right, well, we have to start at 0. So we'd be going 1 to the power of 0 on 0 factorial plus the next x value. X is always 1. The next n value would be 1, right? So we'd have 1 to the power of 1 on 1 factorial. Then we'd have 1 squared on 2 factorial. Then we'd have 1 cubed on 3 factorial. It really all seems a little bit overkill because you probably know that anything to the power of 0 is 1, 0 factorial is 1, so this is just a 1. That's just a 1. 1 to the power of 1 is also 1. This here, 1 squared, we're always going to have 1s on top of these fractions. 2 factorial, that's 2 times 1, so that is a 2, and then we have a half. 3 factorial, 3 times 2 times 1 is a 6. The next one is 24. The next one is 24 times 5, 120. So this would just keep going. For as long as you like, and in fact the n values would go up to infinity, right, to do this sum. You see that at this stage here we're already getting pretty close to what e is, and we'd effectively just be getting more and more decimal places as we kept going with that sum, right? Because here we've already got 2.5, then we plus a sixth, that's, so plus the sixth, that gets you to what, 2.66 recurring, and plus a 24th and so on, and you're going to eventually approach your number e, okay? All right, so that's how that formula works, and that is why in the book they've written this little bit here, right? They're trying to show you how you could do that sum, all right? Now, these exponentials, they're really quite interesting. You might remember in class when we were doing differential calculus, we looked at things like y equals 2 to the x. We would graph it. So in this case, it goes through 1. Y equals 2 to the x. And then we thought about, well, all right, how would we find its derivative? And if you go to a program like Desmos and you do the derivative, you'll see that it comes through slightly underneath that function. Right? In fact, let's do that because Desmos will draw nicer graphs than I will. Have a look. This will be a good revision for you. So I've got this ready to go here. If I had a function y equals 2 to the x, all right, the function here is in red, the derivative is in blue. How do I hide that? There we go. And we might zoom out a little bit, not too much. So there's the function. The derivative looks really similar to that function, right? In fact, it's proportional. And I could show that it was proportional if I looked at the derivative. If we remember first principles, h approaches 0, f of x plus h minus f of x, divide h, right? I don't know why I drew that there. Doesn't need to be there, sorry. In this instance, we'd have our limit as h approaches 0 of 2 to the power of x plus h minus 2 to the x, all divide h. Now, I could rewrite this as 2 to the x times 2 to the h, right? When we add powers, it's like times in with the same base. And I'm just doing that so that you could see that I could pull out the original function, the 2 to the x. It's a common factor in this numerator here. I'll be left with 2 to the h minus 1, all divide h. And where this eventually would lead us to, I don't want to spend too much time on it, but it leads us to this idea that the derivative is actually just some number, right? And this would just be, some numerical value, right? Some number times the original function, which in our case is 2 to the x. And so that when we look at exponential graphs, the derivative is directly proportional, right? This is just some number. And when you have an equation that's some number times x, you've got direct proportionality, okay? So then we thought about, well, okay, is there a function that is exactly its own derivative? Because when we go to 3 to the x, have you noticed that the derivative is slightly underneath 2 to the x here? When we go to 3 to the x, you'll see that the derivative is slightly above. Right, so the blue line, the derivative function line is now above. Right? Is there some magic number in between 2 and 3 where the derivative is the function? And we know there is, and that answer is E. Okay. If I zoom in, I can see some blue dots directly on the function line in red. Okay. Now, how would we? One way of thinking about that is to think, well, there is some number, E, where the derivative equals the function. The way to get to it is to start at the number 1, right? And we'll actually be able to derive this sum by doing this. So if the function equals 1 and I want to have a derivative the same as the function, but I can't get that 1 in the derivative from this number 1. I would need an x, right, to get that 1, all right? But I'm looking for the derivative to be the same as the function. Right? But how would I get an x in a derivative? I'd need an x squared to get that x term. But if I take the derivative of x squared, I get 2x, so I would need to divide it by 2, right? But then I'm making the derivative the same as the function, right? How do I get an x squared term? I need an x cubed. If I took the derivative of that, I'd get 3x. What I really want, I'd have 3x squared. But I don't want 3x squared, I want 3x squared divided by 6 so that I can get back to this, right? So actually need to divide that by 6. Then we can put this into our derivative. Whatever happens up here, we have to put down there. Right? How would I get this x cubed? I'd need an x to the power of 4 in the function, but I need to ultimately have it divided by 6. So it turns out to be 24. The next one will be divided by 120, and so on and so on. And you can just go forever, all the way up to infinity, right? So if you look at these denominator numbers closely, right, we've got these numbers here. Well, this is 5 factorial. This is 4 factorial. This is 3 factorial. This is 2 factorial. We could write this as 1. And we could write this as 0 factorial. And we could get a nice pattern using factorial numbers for those denominators, which is why they're able to just simply write n factorial as the denominator here, right? So that's what's going on with that really interesting sum there. But then the next step is they say, all right, well, here's a probability function, right? And the probability function is, sorry, my pen's having issues again, there we go. The probability function is 0.2 to the power of x multiplied by e to the minus 0.2, all divided by x factorial. Okay, now they say use this definition to evaluate this probability function, right? So what definition are they talking about? They say sum of n equals 0 up to infinity. And you should be, I guess, noticing that it kind of looks like this sum up here. Right, I'm just going to write this out. 0.2, and this is where my focus is going to be for a minute. Okay. All right, so what would be happening if we use this definition to evaluate our probability distribution, which is here? Well, this is a sum, and in this sum, there is a number where every part of the sum is multiplied by. Okay, so this e to the minus, just a number, e to the minus 0.2. There's no n's in there. That's the clue that this is just a number. I could write it like this. I could write it like this. I don't know exactly what it is. I think it's approximately 0.8-ish, but I'd have to check. It's hard enough for me to remember what e is, let alone e to the minus 0.2. So it's just some number, and in a sense, you could say that it's like a factor that we could take out of the sum. Imagine you were summing up these numbers. Let's go up to, say, 10, right? So 2 plus 4 plus 6, that's 12, plus 8, 20. This would equal 30. Well, each of these numbers has a common factor, 2. And I could say, all right, that's the same as this. Plus 4, so 8 divided 2 is 4, 10 divided 2 is 5. Now if I sum all of these, 1 plus 2 is 3, plus 3, 6, 10, 15. And then I could simply multiply by 2 at the end. So I could say this is 15 times 2, and I'll get the 30, right? We can do the same thing with this sum. Right? So we could say that it equals e to the minus 0.2, that common number that's always going to be there, right? You can, hopefully this point's clear. I mean, I could start putting in values of n into this sum, right? And just keep going with it. I've just realised there's a little error here, sorry. That should be an n. That's better. Not sure why I wrote an x. So let's think about that maybe. If I wanted to evaluate this sum, I could say, all right, we have 0.2 to the power of 0. It's on 0 factorial. There's my factorial. It's times e to the minus 0.2 plus, now let's make n equal to 1. Remember the n's are integer values. It's on 1 factorial, e to the minus 0.2 plus, you probably get the idea here, right? Dot, 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 and this just keeps going forever. Okay, but every time for each sum, this number is in there, okay? So I could pull that out of the sum and just multiply it right at the end, right? I could rewrite this as e to the minus 0.2 and then simplify my sum slightly. Infinity, and we'd be left with 0.2 to the power of n on n factorial. And this is where I need to compare this to this. Okay? There's a reason that they started the question by showing you this formula to evaluate e to any power, right? Our formulas, so this part here, the sum, the x to the n on n factorial looks really, really similar now to this sum. The only difference is that we have 0.2 in this position instead of an x. Right? If x was 0.2, then that x would also be 0.2. So what we're saying is that this here has to equal e to the power of 0.2. Right? Therefore, it follows that I'd be left with e to the minus 0.2 times e to the 0.2. Right? We've got the same base, we're multiplying. What do we do with powers when we multiply? We add the powers. Minus 0.2 plus 0.2 is 0. Anything to the power of 0 equals 1. Right? So therefore, this probability function, right, will ultimately equal 1, right? And therefore, it's a valid probability function, right? So your properties of probability distributions are that they would add up to equal 1, right? We could write this like that, or we could write just this, right? And if we were to sum up all the probability values, right? If I was to sum every single value, starting at the first value, going up to the nth value, sum up all my probabilities, and it would have to equal 1, right? Just like this equation does. So therefore, we can think of this as a valid probability distribution. There is another part to a probability distribution being valid, right? Because the individual probability values need to lie between 0 and 1. So valid probabilities, values, or properties of a probability distribution. Let's just say valid probability values, as in individual probabilities. They need to lie between 0 and 1. They can be equal to 0 or 1. That's fine. And with our particular probability function, probability distribution, that is indeed true. Okay, so I'll just rewrite it. E to the minus 0.2. Well, this notation is a bit confusing. Right? So no matter what x is, this will always be positive. Right? So we could say we're always greater than 0. And no matter what x is, the value will always be smaller than 1. And it might be worth actually trying some values to see that. So let's say x equals, you have to do 0 as your first one in part B, part 2. So what would that mean? Times e to the minus 0.2, 0 factorial, right? And you could go to the calculator and you could evaluate what that is. So let's quickly do that. Oh, we've got a lot of stuff here. Let's clear all this. So we want to do 0.2 to the power of 0. Well, that's just 1. The denominator's 1. So all we really need to know is what is e to the power of negative 0.2, and it would equal 0.818. Yeah, I had in my memory that it was about 0.8. Right, so it's approximately equal to 0.819, right, if I round up. Okay, and that will actually be the highest value there, because as soon as I start making x large values, you know, if I was to set x to 100, right, we'd now be dividing by 100 factorial. That's a really big number. So as x increases, this whole function will actually tend towards very small values because your denominator will get so large. So we'll never get values greater than 1. Okay, thank you.